so I can say hello and happy Thursday. Another lovely weather day here in Iowa. February is the worst. For those of you for whom this is your first Iowa winter, it does get better in about a month, I would say. Spring is maybe April-ish, where we can stop having snow and ice every damn day, and I can find my mailbox again, fun things like that. So what I have on tap for today is example 3, which is a brand new example that I just built over the weekend. And I have lecture 4 available that we may start and we may not get to it. We'll see. But as usual, I'd rather do something well than rush through it to do a lot of things. So if you have questions, please do not hesitate to ask. I'd prefer this to be a dialogue as opposed to a monologue, because I know you're all here because you're interested in this topic. This is not a required class. I am very lucky that I don't have to teach many of those. So this example 3 here, is modeling change over time in a latent factor. So we're making use of the actual SEM side of the story to fit measurement models, where I have 3 indicators of a latent variable and 4 occasions of data, and we want to examine the extent to which the latent factor itself shows individual change over time. That's the story. These are the same data. This is from the same data set with the older adults that you're familiar with. It's a different sample. It's more of the sample than we had before. And I have a couple caveats here in the story about the data. I'm pretending that these occasions are perfectly balanced because the code gets much clunkier and uglier when it's not. And I'm also pretending that these aren't twins because I wanted to have as much sample size as possible. So it's hard to do everything right in the rightest way possible all at the same time. So sometimes we have to make some concessions. I'm also borrowing some diagrams and things from the readings that go with this unit. There's 2 chapters from the Grimm et al. Book about modeling longitudinal SEM something or another. I forget what the exact title of the book is. So I want to say that with a caveat because I am going to present some different opinions, perhaps, or perspectives than what they have in the book. I know the authors of the book. I've known them for at least, I know Kevin and Neelam. I've known them for 20 years because I was a postdoc when they were graduate students, and we hung out in the same professional circles at conferences and stuff. So I don't mean any disrespect. But the reality is that there is room for us to reasonably disagree and come to different conclusions about how to do things. So I think it's actually good that you're getting multiple people's perspectives and opinions about what the right way to do stuff is, so that you can come to your own decisions about what you think, and more importantly, be able to defend it to reviewers and to your audience when you're presenting your work. So that, I just lay that out there as a caveat here. So most of you, I think, have had some exposure to measurement modeling in SEM. Carl, have you had that yet?
We have a course coming up.
A course coming up.
Taking classes, just not in the university, outside the university.
Okay, and so if there are folks here who have not had SEM, and I say something that you're like, what the hell is that? Please stop me and ask. I'm happy to clarify. Otherwise, this should sound familiar if you've had SEM for me. This is something I teach here every other fall. I just did it last fall, so it will come back in another 3 semesters or so. Because a lot of this has to do with the SEM part of just figuring out, do you even have a latent factor? And more importantly, for measuring change, can you say that it's the same latent factor over time? Because if you can't say that, it makes no purpose. It doesn't make any kind of sense to say whether the factor changes if it doesn't mean the same thing. So there's lots of examples of how a construct can change over time, or how it, how you measure it would change over time. Some classic examples with children would be things like, if you're measuring disruptive or deviant behavior, you might have an item about how frequently does your child bite people. And that item means something very different if you're talking about a 3-year-old or a 13-year-old. Likewise, if you're trying to give math problems that involve like 2-digit multiplication, like 8 times 9 or something, that might measure math in a 2nd grader, but it probably measures memory in a 12th grader, or at least it should. So just because you have the same measures over time doesn't necessarily mean that they mean the same thing. And some of this is a statistical argument, some of it is more of a conceptual argument, because when you find that the way that your measures relate to a trait differs over time, you have to be able to defend it as a reasonable thing versus an unreasonable thing. So there's a kind of a lot of subjectivity, I think. But there are many instances in which this type of process, measuring change in a latent variable, would be better than measuring change in observed variables. The obvious one is that whenever you're working with an observed variable, we're pretending like it has no measurement error. We're pretending like it's perfectly reliable, and we know that's not the case. So I completely ignore all of the advice that I give during my SEM class in my longitudinal class most of the time, because we're working with observed variables that we pretend are perfectly reliable. When you have the same variable measured over time and you're treating it as observed, you are also assuming invariance over time of how the items that would make up that variable relate to the trait. So you're making all kinds of assumptions that are probably not true. Question?
And so your example earlier about the item that measures biting in a 2-year-old as opposed to a 10-year-old,
Mm-hmm.
is that an instance of measurement invariance or non-equivalence? Or?
Okay, so yeah, so thank you for the question. I got to define my terminology. So if an item relates to the factor that it measures the same way, we call that invariance or equivalence. If an item relates differently to the factor over time or over groups, that is, you would think variance, but no, it's non-invariance. It is the most god-awful terminology ever. Non-invariance is also differential item functioning in IRT world. So I tend to try to avoid that language when I'm talking and I say this is the same or this is different, because those words are much easier to hang on to. Same means invariant. Different is non-invariant or differential item functioning, or diff. So the example then, if you have biting in a toddler versus biting in a teenager, that would be an example of non-invariance, because the way that that item relates to a trait differs across age. Biting is a bigger problem if a teenager does it. Teenagers have bigger mouths too, right? Like that's the other part of it. It's like the same item, like how often do you punch your friends? Well, if a 7-year-old punches his friend, he's not going to do as much damage as a 17-year-old who punches his friend. So the consequences of those behaviors, I think, are necessarily different as well. So those are examples of non-invariance where like you can reason your way to why it should be that way. It makes sense. Situations where you have non-invariance but it doesn't make sense are harder to defend. Okay, did that answer your question?
Yeah, definitely.
Okay.
And just to be sure,
Yes, please.
non-invariant is not equivalent.
Yes. Invariant is equivalent. Invariant, same, equivalent. Not invariant, not equivalent, different. I don't know who made this up, but we need to fix it. That's what I can say. We need to fix it. This is hard enough for a native English speaker. I can't imagine what nonsense this sounds like from folks who are used to different languages. Okay, so yes, so when the same measures are given over time, we want to make sure that they're relating to the latent trait they measure in the same way. That would be one reason to care about this. Another reason is if you deliberately change the measures that you're giving over time, which is necessary to maintain measurement sensitivity. You can't give the same test to measure math or reading or writing or whatever as children get older, because they're going to eventually hit the ceiling and it won't be useful anymore. Likewise, you can't take a test designed for 6th graders and give it to kindergartners, because they're going to all be at the floor and it's not going to tell you anything. So you can deliberately change the way that you measure a trait over time, but then you have to be able to account for that in the analysis. And so these types of models are designed to account for changes in the measurement structure, whether it's because of non-invariance or whether it's deliberate to maintain sensitivity. The key to doing that, though, is that you have to have planful overlap of the measures given. Like if I give test ABC at time 1, and I give test DEF at time 2, I'm done. There's no way to put that back together again. Those are different measures. The right way to do it would be something like ABC, and then BCD, and then CDE. So you're gradually overlaying the tests or the items dropping the ones that become irrelevant because they're too easy, adding ones that are of higher difficulty so that you can maintain the whole thing linked back together again. Terms, you might know that idea as, it's a linking design. In psychology, there's a new catchphrase of integrative data analysis. That's the same thing. Yeah, you're laughing. Yeah, I know. Psychologists like to reinvent words. Vertical linking, vertical equating, vertical scaling, those words. So in testing companies, they deliberately change the tests as the children get older so that they could maintain measurement sensitivity. Am I forgetting any words that should go into this pile? Yeah. Point is, you need overlap. When I was a graduate research assistant at the University of Kansas, I worked in the Lifespan Institute's data analysis unit. And one time, we had an investigator come in, and they had given different tests at like 3rd grade, 4th grade, 5th grade. And they were going to solve that problem by z-scoring everything to put it on the same scale. And we had to say as politely as possible, yeah, z-scores don't grow. They're not on the same scale just because you made them mean 0. It doesn't work that way. So they were not happy with the result of that conversation, but they should have come talk to us in the first place, because we would have said, don't do this. Make some planful overlap. Question from the Zoomers. So does this test happen after the linking process or concurrently as a different analysis? Could be either one. I think that to the extent that you have enough data to do sort of an invariance check at points along the process, if you find things that are not behaving in the way that you expected, that would still allow you a chance to change it or swap something out. Whereas if you waited till the end, you wouldn't necessarily have that flexibility. I would say that this type of strategy of using a latent variable, building a measurement model for it, and focusing your analyses at the latent variable level can also be used in situations where you accidentally didn't give the same measures over time as well. So let's say that you forgot an item on your Qualtrics survey, or someone else used a 4-point scale and then you used a 5-point scale the next time. Like, those sorts of changes can potentially be addressed by working at the latent variable level. So observed variables are great, but we make a lot of assumptions and they don't have the flexibility that latent variables can. That being said, you need a shit ton of people to pull this off. The more complicated your model, the more people you need. And yes, that is a technical term, a metric shit ton. I've had a lot of caffeine today. I think I need to just like take a break here. Questions as I take more?
My question is about the tests being related. What if increasing the number of items, does it matter such that the example you've given there are like same number of items across the test? What if you have like 5 items on one, 8 items on the other one, 10 on the other one?
If we change the number of items across time, but we also change which items they are simultaneously, theoretically, the more items you have, the better you're going to measure, assuming that they cover the range of the trait that you're interested in measuring. I don't necessarily see a problem with that unless the fact that you have better reliability at some occasions would maybe constrain what you can predict. Like you won't have as good of an estimate of the intercept if the intercept, like at that occasion, is not measured as well as you would if you put the intercept at the end of the study, if you had more measures at the end, something like that. There might be some caveats that you would have to make, but I don't necessarily see a problem with changing the number of items. Overlap is the key. You need overlap. Mathematically, you need 1 to stitch it all back together again, 1 item in common, but that is a terrible idea. I've got 3, so you can see what it looks like here. I chose 3 because 3 is the number of measures in which a latent trait is identified, meaning that it is mathematically solvable. So it is the bare minimum that you would need to be able to make a latent trait in the first place. Only having 3 items, though, does not allow you to test whether those 3 items have a pattern of correlation that's consistent with a single latent trait. You have no other choice. You have to believe it. Because I have 4 occasions, though, the first model that I'm going to estimate is a joint model of a latent trait at each occasion, each measured by 3 items, 3 tests in this case. So I am, again, making some constraints here. That way I can actually test whether the measures are consistent with a single factor at each occasion. That does become an over-identified model. So I have degrees of freedom left over. Okay. Other questions about just the general philosophy setup before we dive into specifics? This could be its own course, right? Like the idea of combining measurement and longitudinal stuff could be its own thing. But I got a little bit of it because I know that a lot of you are interested in doing things like this. So I wanted to give you an example. I am using, so this is based in a confirmatory factor analysis type of setup. So I am using actually test scores. The three measures that I have is a block design test, which is a measure of abstract reasoning, digit symbol substitution, which is a measure of processing speed, and prose recall, which is a measure of memory. So in this sample, those are consistent with the single latent factor of cognition. That may not be true at different ages or different samples, but here I can say that. So each of these is a test score, not a single item. That makes it a little bit more plausible that saying that these test scores have conditionally normal distributions and have a linear relationship to the latent trait is a reasonable thing. That's chapter, I think, 14 of the Grimm book is this type of model. If you're modeling item responses, so binary or categorical item responses, then the next chapter 15 has examples of how to do that. And I can help you with that too if you're interested. Okay, so I'm using M+ today. The data for this example are not online, but all of the syntax and output files are, because these are real data and I don't have permission to share them. So I made a CSV file for M+. This is a wide format file. So this is a single level structural equation model in which all of the data for each person is on a single row. So I made this separately rather than trying to do it within the program. So I have the names of the variables in my data set first. Case is my ID variable in this setup. I have age at time 0 because I was on the fence whether I wanted to include it and eventually decided that since this handout is already 19 pages long, I didn't need to go there. But I have block design measuring from times 1 through 5, digit span 1 through 5, and prose 1 through 5, but then I ended up deciding to only use 4 occasions. There's 2 practical reasons for that. One is so that it would match the pictures that I'm stealing from their book, and the other is because the 5th occasion had a whole lot of missing data, so I decided not to use that. It is not a coincidence that each of my names has 5 characters. I always name my variables so that they have the same length if humanly possible. That way my code stays nice and aligned and it's much easier to troubleshoot. So that's just me being sort of idiosyncratic, but it helps me read these things more clearly when I come back to them. So in the type here, this is a general type of model. Other kinds would be like 2-level or have a complex sample if you need to correct for clustered sampling or stratified sampling. I am using MLR estimation, which stands for robust maximum likelihood. This is still ML in the way that we know it. So it's still full information, maximum likelihood. The R part is an adjustment to, what R does, I should say, is an adjustment to the parameter standard errors and all of the fit statistics for deviations of multivariate normality. The Ender's Missing Data book, chapter 5, explains this really well. And I have that chapter on basically every class's reading list. So it's in the SEM class, it's also in the longitudinal class from last semester. Basically, if data are multivariate normal, there's some ratio of first derivatives to second derivatives that holds. And to the extent that that doesn't hold, then the difference in what it should be is like their correction factor. That's my very general understanding of this. Like I said, he does a better job of it. But I'm doing that because probably these outcomes are going to have some skewness to them, and it's a reasonable thing then to fit a robust estimator for this. Worst case scenario, actually I should say best case scenario, if this is overkill and multivariate normality holds perfectly, then this simplifies to the ML solution. So I'm not hurting anything by adding this. It would have a scaling factor of 1. As we'll see in the output in just a minute. Other things that I'm asking for in the output, residual is an option that tells us what the model says the predicted means, variances, and covariances should be according to my model, and what the discrepancy is in each of those relative to what they are in the data. So it's a way that if there's parts of my model that don't fit well, this helps me clue in as to where the mismatch is between the data and the model. Modification indices, these are score tests, for those of you who are familiar with that term. They are, hey, you know what? If you put this extra thing in your model, you can decrease your chi-square by this much, and here's what it would be. So I call these cheat codes. That's the term that I've settled on. For those of you who play video games, the idea that you can get, some additional help, not by your own merit, but just because you know where to find the cheat codes, that's what these are. They are completely atheoretical, and you should consider them with caution. However, in this context, what I'm going to be looking for are them to tell me which of the invariance constraints is causing a problem. So I'm looking for these just to say, like, what are the extra layers of equality that I've put on my model, and where might those not hold? They can tell me that. Standardized solution, I don't think I'm using it in this example, but I typically have this when I do SEMs. That puts everything in a correlation metric. And Tech4 is a piece of output that spits out means, variances, and covariances for your latent variables specifically. So that output can be helpful in conceptualizing what the growth model is actually trying to predict when it comes to the latent factors themselves. Okay, questions? Oh, 6635. This is the minimum chi-square value that I want it to print. So it's not going to print any suggestions that don't meet that minimum. That corresponds to an alpha of 0.01 for a single degree of freedom. So I'm asking for things that would improve the model at p less than 0.01. Okay, other questions? All right, here's my model then. Here's a picture of my model. Now, interestingly, in the book, they only had 3 outcomes too, right? But they have a picture with 4. So do you have any idea how long these pictures take to draw? They can take forever. So I was like, screw it, I'm just going to fix it. So just pretend that this box isn't here, okay? Problem solved. So I will point to the parts of the picture here as we go through the layers of code under the model section. In M+, the green with the exclamation points are comments. So that's all just notes to help you understand what that part of the code is doing. So I am defining 4 latent variables by the keyword by. That's how you tell it, make these indicators load on these factors. I've named my factors T1, 2, and 3, and 4. The first occasion, second occasion, third occasion, fourth occasion. You can name them anything you want so long as it's 8 characters or fewer. I have the time 1 with the 1 at the end of the name here, time 2, time 3, time 4. So I would also encourage you to keep your naming system such that you can easily hit find and replace and see what, like if it's item 1 versus time 1, like have a consistent way of writing that. I have stars after everything that is going to be estimated. So I'm asking for all of the factor loadings, all 12 is what I'm going to have here to be estimated. Technically speaking, I don't need the stars except for in the very first case. I do need the stars after the first item that is measuring these factors. Because if I don't, M+ will fix that loading to 1 against my will by default. So the star overrides it and says, hey, no, estimate that, please. So in this system of equations here, which is what this is actually writing, T1, 2, and 3, and 4 are predictors. Latent factors are predictors. They each predict 3 outcomes, 1 for its occasion, 3 per occasion here. So this model has essentially 12 outcome variables at the same time. What I'm saying is that the pattern of covariance among those 12 items is consistent with this 4-factor solution, where the factors are also allowed to be related. So this T1 by thing and the picture, this is depicted by the circles to the boxes. So the loadings right here are the labels on these directed arrows. They decided to go with, I think that's Eta, is that right? Okay, yeah, my Greek letters are not very good. I only know like 6 of them, but this is another one I can't draw very well, so it doesn't make its way into my notation system. But they went with Eta. So now what we have is taken these circles, given them a name, and then added the arrows going to the boxes so far. Okay, with me so far? Yes?
Just basically means latent cognition at time 1, time 2, time 3, and time 4.
Yep, my cognitive status at this occasion is theoretically responsible for how I answer block design, digit symbol, and prose recall. That's what I'm saying. Another way to say it is that this is kind of like an R matrix structure that we had last semester, where we had like autoregressive and Topolits and stuff. A factor model is another way of predicting a pattern, where you're saying that the total variation in each of these outcomes is partly due to the factor, that's the common part, and partly due to error or unique variance that's uncommon. And to the extent that these factor loadings can recreate the covariances, then you're right. So this is another kind of correlation pattern, essentially, that we're invoking, but it's done with these specific directed arrows from the latent factor to the observed outcomes that say how related those are. So those are slopes. These are regression slopes. Loadings are slopes. It's just that the circle is imaginary. What we've done basically is take the covariance among these 3 outcomes, put a circle around it, and given it a name. Time 1. Okay, next layer. So I'm defining the first 3 blocks of code here, by the way, are the measurement model. You can interpret these sort of like paragraphs because each block is doing a different thing. The next is the intercepts. So each of these variables has some mean associated with it. We are turning that into an intercept instead. Now I know we're talking about latent variables, but the definition of intercept is the same as when you learned it like in 8th grade, and the same as it's been in every other class you've had with me. What's an intercept?
Predicted outcome when predictors are 0.
Predicted outcome when all the predictors are 0. Expected outcome, predicted outcome, whatever terminology you want to use. So what this is saying is, what would the score of block design be if the factor score were 0? Because the factor is the predictor in this situation. So each of these observed variables, all 12 of them, is going to get a separate intercept, and it's estimated. Likewise, we know that the factor isn't all the reason for the variability in this. There's something left over. So we have what are known as error variances or residual variances, and those are, I'm laughing because they're these curved circles under each of the boxes, but it looks like a devil's pitchfork in the way they drew it. Like, this is evil error, not just error. The SEM world loves to invent synonyms for this idea. You will hear the term error variance, residual variance, unique variance, specific variance. It's not the factor, right? I don't care what you call it. It's not factor. It might be error, it might be something specific, but you don't have enough information to pull those things apart. It's whatever's not the factor, whatever variability is left. Reasons why somebody would score higher than someone else besides the factor. Could be error, could be something systematic. We don't know. We don't care. That's not our job today to care about that. Next layer. Same occasion residual covariances, which do not appear to be in the picture. That would have cluttered it up quite a bit. What we are allowing is basically the same measure over time to have an additional covariance because it's the same measure. The width statement here allows all possible pairwise covariances. So like this single line, given the 4 outcomes for block design, is introducing 6 covariances, all possible pairs. That is a standard thing that people do in these models that seems to make sense. Like, because this is literally the same test, it should be more related beyond just what the factor is at that occasion. You could put constraints on these or remove the ones that are non-significant or otherwise sort of trim that part of the model down if you felt like it, but I'm just going to leave it there and focus on the rest of the measurement model. Okay, then we get into what I would call the structural model, which are the parameters that relate to the latent factors, means, variances, and covariances for the latent factors. Oh, I forgot. In the picture, the intercepts are the paths from the stupid triangle thing here. This triangle convention is something that I really hate, but it's introduced to be able to put a place to put the intercepts or the means in a picture. They gave the intercept, the one column of variance, which I do not understand. That's probably a typo. But this one refers to the idea that, like in matrix notation, if you were to multiply, like if you need a column in your design matrix for what the intercept would be, that would be a column of ones. So that's like what they're trying to represent here, is this a column of ones. So their intercepts are tau, I think. Not to be confused with tau equivalent, which is what we call equal loadings, not equal intercepts, but whatever. Everybody gets to pick their own notation. And then they have, I'm going to go with, what's that one? What are the errors?
Theta?
What is it?
Theta?
Is that theta?
I think so.
Yeah.
That's theta? Okay, thank you. Theta is the latent variable. Come on, people. See, it's bad enough when we have to use Greek letters, but it's even worse when we can't agree on what they mean. So notation is always author specific. I just need the code, right? Like the picture is helpful, but I just need the code to figure out what's going on with this stuff. Okay, that's where I was. I realized I had forgotten to talk about the triangle when we talk about latent factor means. So at this point, all of the factor means are fixed to 0. That is an identification constraint because we estimated all of the intercepts. So it's either one or the other. Either you can have a factor mean be estimated, which means you have to force one of your intercepts to 0, or you can estimate all the intercepts and force the factor mean to 0. The latter is usually more common in an SEM framework. So that's why the triangle thing doesn't have any paths up to the factors, because it doesn't have means at this point. Variances. These are also fixed to 1 for identification at this point. So you can either fix one of your loadings to 1, or you can fix a factor variance to 1 to identify the scale of your factor. So identification is referring to the idea that these latent factors are imaginary variables. We have to give them a scale in order for the rest of the parameters to be found. And the scale that we give them is irrelevant. Like, we could say the mean is 50 and the variance is 10, and it'd be like, sure, and all the other parameters would rearrange themselves accordingly. But 0 for the factor mean and 1 for the factor variance is very common. That way a standard deviation is 1. That refers to the curved arrows up here, to which I have added 1s in the blue font here to indicate that these are all fixed to 1 at this point. And last but not least, how you did at time 1 is probably related to how you're going to do at time 2, 3, and 4. So we allow 2-headed arrows, which are covariances between the factors. And that happens with the very last line of code right here. Okay. Questions?
Lisa, I'm still really confused about the triangle.
Yeah, me too, dude. What's your question?
So that triangle, because there's arrows coming from the triangle pointing up to each one of the observed, like the
Oh,
Y's.
they did do it these
Then
ones.
there's also taus.
Okay, so it does look like they tried to put factor means over here, but they have to be fixed to 0 for identification if they have all the intercepts, which they do. So this part should be 0. They're using alpha for a factor mean, it looks like, rather than a tau thing. Okay, that was the first part of your question, right? Was there a second
I
part?
think so. The one is, like, is that referring to the variance for each one of the observed
No,
variances?
no, it's
No.
referring to its intercept. So the triangle thing is responsible for introducing intercepts and means into the model.
Okay. Interception means for the factors.
For anything. So
For
it's,
anything.
it's an intercept if it's for a variable that's being predicted, such as our 12 outcomes. It's a
Mhm.
mean for a variable that is currently unpredicted, which is the case for the 4 factors.
Okay.
The variances for the individual outcomes are what looks like devil's pitchforks here, but it's actually because the intercept line is in the middle of a curved arrow.
Okay.
Yeah, so the curved
So-
arrows mean variances.
The 8011, for instance, so that's including both the random intercept and random slopes.
There's no random intercepts and slopes in the story yet.
Okay.
These are just 4 factors going about their business. They're not changing. They're each identified on a separate scale, so we can't even compare anything yet.
Okay.
Okay, does that help?
Yes. Yes. So there's yet another level that we have to add in to get to the random intercepts and slopes.
Yeah, that's like 17 pages from now.
Okay. Then I think I understand it, I think.
Okay, yeah, it's coming, but it's the finale of the series here. It's the grand finale when we get there. Right now, we just got 4 factors. They're not on the same scale yet because they're each identified with the mean 0 variance 1. This is like the person at KU who z-scored their stuff. Z-scores at time 1, z-score at time 2, z-score at time 3. That's what I have here so far. The purpose of this is not to test change. The purpose of this is to see if these 12 outcomes are consistent with the idea of 1 factor per occasion that's related to each other. So this is what's known as a configural invariance model. That's where we're at. Yes.
I have one more question.
Mhm.
So last semester in factor analysis, we saw that, for example, to compare between groups, we had to list the model, specify the model, and then compare between groups with a variable that divides between groups. But now we must list all the components for all the models, all the measurement models,
Mhm.
and then run the analysis.
Yes. So the question was, why isn't this a multiple group type of model? And it's because the factors are repeated measures. So in that case, we don't have like a model this and a model that, the way we would for multiple groups. Everything is in one model, because otherwise there would be no way to allow the factors at different occasions to covary, and they have to. So another way to say that is a multiple group model is enforcing uncorrelated factors across the groups. And that makes sense if these are entirely different people. It does not make sense for any kind of repeated measure situation.
Could we introduce differences between groups? For example, say gender between,
Sure.
and that would be some kind of level or additional layer for the analysis.
If you wanted to split this by gender, then it would be a multiple group model, assuming that you're lumping people into gender groups as opposed to some sort of continuum. Like if you wanted to do like men versus women, this would be a multiple group longitudinal invariance model.
Yeah, great.
And then you would have the potential for, like, if you think of it from like an ANOVA kind of perspective, it's a 2x4 with respect to the factors, because it would be 2 genders by 4 occasions, and then you could have invariance constraints by gender, by time, and then interactions, like, and that's enough. This is already 19 pages, I can't.
Yeah.
Yeah, but one could.
Yeah.
Not today, though, but one could. Okay, yes,
Maybe a silly question, sort of going backwards a little bit, but
not silly.
the triangles, the taus, is that not the mean of that observed indicator?
It could be, but it doesn't have to be. So if you have an identification of your factors where the factor mean is 0, then yes, the outcomes intercept will be its mean.
Which is what we have here, right?
Which is what we have here.
Okay.
But that will not be the case when we allow the factor means to differ from 0, because the intercept is the expected outcome when the predictor is 0. So it does work out to be the indicator means. Sorry, I'm slipping into CFA language. Outcome means. It does work out to be that in this case, but that's not generally true. That is, a common misconception because people use the term like, I'm going to do an SEM with a mean structure. And they mean add in the stupid triangle stuff. Because when SEM was first invented, they mean-centered all of the variables to remove all of the mean information because it wasn't part of the story. So adding the means back in happened later. But it really is intercepts for anything that's being predicted is the way to think about it. It's not a mean anymore. Okay, other questions? And no, it's not a stupid question. Nothing's a stupid question. I might give a stupid answer, but that's a different problem. Okay, so this is my configural invariance model. The purpose of this model is to just see whether the factor structure that I've put forth is reasonable and adequately recreates the means, variances, and covariances of the data. That's my job here. If it doesn't, basically I need to make it fit until, or else it's game over. Yes?
Yes, one additional question, Lisa. In
Yeah.
this case, what kind of structure are we using for the residuals? Unstructured?
Not unstructured. The residuals for the outcomes from the same factor are uncorrelated. But the outcomes from different factors that are the same test over time do have a residual covariance. That's this chunk right here.
Okay. Which is the same, right? We are fixing that covariance for the same item over time to be the same. Or not
No,
yet?
no,
Ah,
there's
not
no
yet.
constraints on that.
Okay, yeah.
So there's 6 covariances implied by
covariance.
each of these lines because
Yes.
it's between the 4.
Okay.
Yep, I have no constraints on that. One could if you wanted to save parameters, but I'm not going to yet.
But that's not unstructured. So we are estimating all of those things, but that thing is not unstructured.
No, because there's a whole lot more. So we don't have any covariances among the outcomes at the same time. We don't have any covariances of different outcomes at different times.
Okay.
And you would quickly run out of degrees of freedom if you tried to add a bunch of stuff. The other problem with that is that the more residual covariances you add, the less you can be certain that you have this as your factor. Because the factor's job is to replicate the covariance, and if it's replicated with residual stuff, it's going to steal from the factor. So ideally, you want as few residual covariances as possible. The alternative, by the way, which I don't think they talked about in their chapter, but which I've seen, would be to fit a method factor. So you might have like a block design method factor that would have 4 loadings to its things, and that would be 4 loadings instead of 6 covariances. If you could take that block design factor and constrain the loadings equal, then that would introduce a constant source of covariance for just like, because it's block design, and that would be 1 parameter instead of 6. So that would be another reasonable thing to do. I was just talking to somebody in office hours about this yesterday, so if you're here, that's what I was talking about. So that would be like another circle here that would go to block design at each of the occasions, and then that would introduce, basically that would be a factor way of introducing these residual covariances. That would be called a method factor or a bifactor model. Specific factors, other words like that. Basically, it's like whenever you have your construct, but then you have extra stuff that you need to account for, you can do it with residual covariances or a factor in these models. Okay, so I gotta tell you, I ran this and I about fell out of my chair because it fit on the first try. That has never ever happened to me. So this is like as good as, literally as good as I've ever seen, and this is real data. Seriously, could not believe it. So that made my job a little bit easier. So I have some notations here on the output. These are indices of absolute model fit, which you're familiar with, but not under that name. So the idea of the answer key model in longitudinal, which like the saturated means are the answer key for what the fixed effects are supposed to do. The unstructured R matrix is the answer key for what the random effects and residuals are supposed to do. That's only possible when you have balanced data. Essentially, this H1 model right here is how well the saturated means unstructured variance model would fit for these 20 outcomes. In SEM language, it's called the saturated model, and this is log likelihood. So bigger is better. HO is our model. It's whatever you said it was. And can I tell the story real quick for those of you who haven't heard it? Okay, it's one of my favorite stories. I used to get this confused because HO and H1 are not terribly informative labels. And I would get like, is this the null hypothesis? Is my model the null hypothesis? Or is the other model, like, didn't make any sense to me. And then one day in office hours at the University of Nebraska, I used to do it in a computer lab where there were like 24 people in the room all working on homework from 2 different classes at the same time. And I would float around and answer questions. And I was talking to someone, and one of my students poked her head up. Her name was Lindsay. Hi, Lindsay, if you're listening. And she said, am I the hoe? I'm like, what? In N+, am I the hoe? You mean, is your model the HO model? Yes, Lindsay, you are the hoe. And she went back to work. And after that, I never forgot it. So just think to yourself, no, I'm the hoe. I'm the hoe. H1 is the saturated model. So maybe a tasteless joke, but it was funny. That's what she said. Am I the hoe? She's not the hoe. She's actually a lawyer who has a PhD. She was in the social psychology program where she did 2 degrees. And so she worked very hard and has been very successful. But she is the hoe, according to this is her model. The scaling correction factor is also something new. This is the amount by which your outcomes deviate from multivariate normality, and this number would be perfectly 1 if it were fine. So this number is used in conducting rescaled likelihood ratio tests for model comparisons. Within the download packet for this example, I have a spreadsheet in there that I built to do this stuff. You can also do it directly in Lavon if you use the M+ automation package to run things back and forth. I haven't played with that yet, but I know people like it. So this number and this number basically tell us how well does our model fit. This is how well is the perfect model, and then we were looking for our model to be not worse than perfect if it fits well. That is what the chi-square test of model fit is telling us directly. This is the likelihood ratio test for how much worse than perfect we are after adjusting for the scaling factors and non-normality. And my chi-square test statistic is 27 on 30 degrees of freedom, which yields a non-significant p-value. And this is a sample size of like 650 people. So is this good or bad, folks?
Good.
Yeah, non-significance is good in this context because it means that we were able to adequately recreate the means, variances, and covariances for my 20 outcome variables, but save 30 parameters in doing so. My factor model is 30 parameters simpler, and it's not worse. I win. Information criteria are also here. You're used to seeing these, AIC and BIC. These are still in smaller is better form because they start with -2 log likelihood, and then there's an adjustment for number of people or number of parameters and stuff like that. It tries to warn you, so the chi-square value under these estimators cannot be done in the regular way, and so that's why I have the modified spreadsheet to add in the correction factors, and they have some section on their website about how to do this as well. So just to remind you that when you're in MLR, you can't just take the straight difference in -2 log likelihood. Then we get into what are known as the other absolute fit indices. These are not part of our story when we do multi-level models, although they could be. There's nothing that stops us from computing those if we have an answer key model available with which to compute them. So these are not necessarily going to agree because they're based on different references. RMSEA and SRMR are both comparisons relative to a saturated model, where 0 means it's perfect and you want your value to be as small as possible. Root mean square error of approximation, RMSEA, is how far off basically you are in terms of your average parameter divided by the degrees of freedom you have remaining. So it has a penalty function for adding stuff that doesn't really help as much. So RMSEA, as we apply constraints to make things the same and save parameters, should get increasingly happy with us. But it's already 0, which is crazy. Likewise, SRMR is how far off on average are the correlations in your model, and this is 0.01, so it's recreating the correlations to the 100th decimal place. CFI and TLI are from a different perspective. This is, okay, so rather than comparing to the best possible model, what if we compared to like the worst possible model? And how much better are we than the worst? So this would kind of be like relative to an empty model, where that's the worst you could do, like how much better have you gotten? And CFI stops at 1, TLI can go above 1, but in this case it's 1, so this is as good as it gets as well. This chi-square test we can completely ignore. This is comparing whether the saturated model is better than the worst model, which, like, who cares? Neither of those have to do with us. So I have that here just to tell you, don't worry about it. I'm not going to print it for the rest of the models. So all of this indicates I win. Yes, sir.
And so typically when we look at, we want low p-values, but this probability RMSEA less than or equal to 0.05, that's a 1. That says,
Yeah,
it's
so
less than 0.05.
it's definitely less than 0.05. Yes, so this, by the way, this p-value has a special name. It's the test of close fit, because 0.05 is like a reasonable amount of misfit that's not terrible, whereas the p-value that goes with your chi-square is absolute fit. And both of these are telling us, yeah, it's pretty good. It fits pretty close to what the data are. So I win. Here's the output. So estimate is the first column, like usual, standard error. Estimate divided by standard error is treated as a z. There's no degrees of freedom in this story, and the last column is the p-value. So the first thing it lists are my factor loadings. These are regression slopes. So I would interpret these the exact same way as I would any other slope on Earth. For instance, the slope for block design at time 1 is 6. So for every unit higher block design, my factor score goes up by 6. That sounds right, right? Nope, I'm backwards. Thank you. This is why I'm like, that doesn't sound right. It's the other way around. See, I was tricking you, seeing if you're listening. I think I've come like down the other side of the caffeine curve where now it's making me dumber. I should switch to water. Hang on here. I bring my water bottle and I never take any. Okay, let me go the other way. For every unit higher factor score, because factor is my predictor, my block design test goes up by 6. That sounds correct.
Yes, but we are using a standardized factor, so that 1 unit difference would be one standardized one.
Yes.
One is D more, right?
Yes, for every standard deviation higher in the factor, the block design test goes up by 6. Yeah, because that's the reason why people pick variance of 1 as their identification scale, because it makes that type of statement easier to digest. Yeah, so let me try another one. Let's see, block design at time 2. For every unit higher factor score at time 2, block design goes up by 6.4. But I cannot say that block design has a higher loading than this one because these are not on the same scale yet. It looks like if I were just to eyeball these numbers, I'd be like, wow, digit has a higher slope. Can I say that? No, because these are unstandardized. We have to know what a unit is in digit and a unit in block is to be able to think about, like, is this a stronger slope? Digit design has a wider scale. That's why it's 10. So these are the loadings. Turn the page here. Factor covariances. This is how highly related the factors are over time. So with respect to the structural model, then these are the covariances that the random intercept and random slope are eventually going to be trying to recreate. So in the same way that our lower order factors are recreating the covariances of our observed outcomes, any higher order factors are recreating the covariances of the lower order factors. It works the same. These, because all of the factor variances are currently standardized to 1, these are correlations. So yes, if you did well at one occasion, you did well at all of the occasions. It looks like this is a fairly consistent trait. Next, we have residual covariances for the same outcome over time. We just let these be. They're all positive and most are significant. So like block design 1 with 2, that means that after controlling for the influence of the factor, however you did, like in your residual of block design 1 is related to your residual of block design 2. Maybe you're just really good at abstract reasoning, or maybe you're really bad at it, like me. I'm really, really bad at block design. I can't do any sort of like matrix reasoning problems that involve spatial ability. I cannot. I get lost in a closet. I am of that kind. All right, factor means. Next section here. These are 0, as well they should be, because I fixed them there. 999 is not a number. It's a shrug emoji. I can't divide by 0. Outcome intercepts. These are the means of the outcomes because the factor means are 0. But I'm going to stay with the word intercept. These are the expected score on each of these outcomes given a factor score of 0. So it looks like if I just eyeball these that people are declining over time, but I can't come to that conclusion yet because these aren't on the same scale. Factor variances are also 1 because that's what I told them to be. Leftover variances last up. This is the amount of variability in each outcome that is not predicted by the factor. Leftover was the word that I would use. Okay. So we have configural invariance. Hooray. Now we can do the layers of constraints to see if it's the same factor over time. What we know thus far is that a factor is consistent with the correlation at each occasion, but we don't know if it's the same factor. So we're going to add layers of constraints to be able to say that. First, we're going to take all the factor loadings and make them equal, see if that hurts fit. Then we're going to go into intercepts, see if that hurts fit. Residual variances, see if that hurts fit. So at every step here, our goal is not worse, because we are taking model parameters away by simplifying things. And we're using rescaled likelihood ratio test by which to do so. I have another whole set of about like words and examples on testing invariance. I have 4 different examples in my SEM class that I'm referring you to here if you want to see more about that, if you haven't seen it before. Okay, questions? Yes?
So is there any like specific thing that we're looking at to say we got equivalence? Or
Not yet.
okay.
We don't know that yet.
So like I was thinking like in the section of the output that exhibits the factor loadings, like those are all relatively similar, just eyeballing them.
Mm-hmm.
And if we saw, for example, like T1 by block 1 is 6, but then T2 by block 2 was like -10, that would be like, whoa, something happened here.
It
right?
would be. So
Okay.
I think that, like, basically we can't say that these are on the same scale, but they should be proportionate to each other. And yeah, if something loaded at one occasion and it didn't load at another occasion, that's a red flag that that item is not going to work the same way over time. And you'd either have to say, okay, I'm fine with that, and let it be that way, or you'd have to, like, kick it out or do something about it.
And if we saw that, we would probably see in the next section of our output the factor covariances. Those would all be really low, right?
Not necessarily,
Okay.
because we don't really know what the factor is. Like, I'm calling it cognition, but the problem could be, like, cognition could be driven more by memory initially, but then change to become more reflective of speed later on. And then it's not the same flavor of cognition. So if it's like memory-based cognition easing its way into speed-based, then trying to see if that factor changes doesn't make much sense. So we know right now that a factor is responsible for each of these sets of correlations of items at the same time, but we don't know that it's the same factor. The loadings are basically how we would decide it's the same enough. Okay, does that help?
Yeah.
Okay, cool.
Thank you.
Sure. Other questions? Zoomers? I can only see one of you. Everyone's quiet today. No? Quiet means good, right? There's some thumbs, yes. Because quiet also means asleep. Or not here, as it turns out. All right. Where were we? Okay, yes. So now we're in the invariant story. And so I tried to make it easy on us by color coding this shit, okay? So things that have changed are in yellow. The next layer will have its own color. So the terminology that we're using here is this is a metric invariance model. That is a term that means all of the loadings have been constrained to be equal over time for the same outcome. So that shows up in a couple different spots in the code. First and foremost, I have used labels to apply constraints. So in M+, if you see words in parentheses before a semicolon, that means one of two things. Either that is the name of the parameter, that you gave it a name so that you could do math on it, like to make a linear combination or to make something else out of it, just like we do. That's the equivalent of like an estimate statement or a lincom or something. We can do that in M+, but you have to name your parameters first. If parameters share the same name, though, then that's a constraint. So I have BL, DL, PL, where L stands for loading, and the first letter is which outcome I'm talking about. So the fact that I have BL in the first spot here means that I am saying the loading for block 1 on T1, block 2 on T2, and so forth is the same over time. So rather than having 4 numbers, I'm asking it to come up with one that's supposed to hold for all 4 of those outcomes, the same outcome at 4 occasions. I'm doing the same thing with DL and PL. Intercepts stay the same, residuals stay the same, residual covariances stay the same. So I have added a little graphic here to say that's what has happened, is that my loadings now have this constraint pattern to them. The other thing that I have to change, though, is to not enforce a structural constraint at the same time that I'm adding this loading constraint. So I have now allowed the factor variances after time 1 to be estimated, and that's why I've added a little yellow star up here to these things here. The rationale is that part of the reason why the factor loadings could have differed over time is because the factor variances wanted to differ over time. That makes sense if you think about it from the idea of a loading being a slope. It's a change in y for a 1 unit change in x. Well, if what a unit is in x changes, then the loading has to change too. If the standard deviation is higher, the loading has to reflect that. So part of the reason for the differences in the loading could have been what a unit should be with respect to the factor as a predictor. If it's only that, then introducing these constraints but allowing the standard deviation to change as needed to adapt shouldn't hurt the model. But I have to keep the factor variance at time 1 fixed to 1 for identification. So now all of the loadings and all the factor variances are on one common linked scale over time, where 1 is the reference. Everything else stays the same. Okay, does that make sense?
So bigger than 1 means more variance?
Yeah. So if people were spreading out over time, you would see the factor variances increase. If they were coming together, you would see the factor variance decrease, where 1 is the baseline. So 1 doesn't mean anything other than that's the scale of my model. Survey says, here's my output. So the first thing it tells you is how many free parameters there are, and that means free to be non-zero. And it was 60, now I'm at 54. So I have a note here as to where the savings of 6 came from. I used to have 12 loadings and 0 factor variances. Now I have 3 loadings and 3 factor variances, and so a net savings of 6. So I've simplified by 6. I do the -2 log likelihood comparison of the HO from my current model relative to the HO of the previous model. So this is one we have to do ourselves, and M+ does not do that for you. And I have a summary of what was in the spreadsheet here. Does it fit worse? The answer, sadly, yes. So p-value of 0.02 means that taking those 6 parameters away made the overall model fit significantly worse. However, the model still fits as a whole. So this is where reasonable people might disagree about what to do. In the book, they argue that because the model still fits reasonably well, that they can ignore the fact that we have some non-invariance here. Homie, don't play that. That is an In Living Color reference from like 1992 for those of you who are old enough. Homie, don't play that. I know the model fits really well, but I just made it worse. So I think I should do some due diligence to figure out why I made it worse. And that comes from a piece of output that I've put here called the modification indices. So they have suggested 3 things with respect to the factor loadings that would improve my model. 2 of these make 0 sense. They want the outcome for prose recall at time 4 to be predicted by time 2 and time 3. No. I'm just going to say no to that. But it also wants the loading for prose recall at time 4 to be predicted by the factor at time 4. Which it's like, hey, it is. Ooh, it already is. What do you mean? No, it wants to have it more predicted, meaning that loading wants to be free from the other 3. So what it's telling me is that if I let the loading for prose at time 4 be different than the loading for prose at times 1, 2, 3, that loading is expected to be higher by 0.3. So given the scale of these loadings, let me find the loadings here. Here they are. The loading is like 6, so it wants a very small difference. I'm willing to let it have it. So that's what I did next. But the rest of this indicates pretty good fit.
Lisa,
Yeah, and there's the solution.
in the case, well, for the modification indices, can you go back?
Sure.
Because that 7.28, that would be the reduction in the R square for that model.
Not the R-square, but the chi-square.
Sorry, yes, the
Yeah.
chi-square. for
Yeah, this
that
is the
model.
predicted improvement in the chi-square if I let this loading be different from its other 3.
Yes, so for example, right now, what's the value of the chi-square for that model? Because
So it's
that
41,
number- okay,
and it used to be 27.
okay. So in this case, something reasonable to us would be something like we want these both models to be comparable or similar. So we want to reduce the chi-square of the second model, trying to reproduce or recreate this version, right?
Yeah, so 27 versus 41. I can't do the math in my head with the scaling factors, but if I just look at that much, that's a difference of like 14.
Yeah.
That modification index is saying one
Almost the
parameter is
same.
responsible for half of that.
Yes, okay, got it.
And to me, that's salient. And now, it's not a big difference. Like, I would still come to the same conclusion about block design or prose recall mattering. It wants it to be a little bit different.
Yeah.
So I'm okay with that. So that's what I decided to do next. But here's the output that's relevant to us from the full metric invariance model. So when you're doing this, by the way, always check your output to make sure that the constraints you asked for are actually there. M+ sometimes doesn't understand. So this 5.9 is the loading for block design at every occasion. 10.4 for digit span, and prose recall is 3.4. So it wants to be higher by like 0.3. I can live with that. The other thing that's relevant to note is the change to the factor variance. So a factor variance of 1 sets the scale of identification for our model, and it looks like that the variance is increasing over time. So people are becoming more different from each other. Another way of saying it is that differences in what a standard deviation is are responsible for differences in the factor loadings. That's what we're trying to say. All right, so then partial invariance, change it right there. That's the one change. Yes?
Yes, can you go back to the variances, please? Because in that case, we can see that the variance increases over time. But in those cases, those numbers are comparison between specific data points or specific latent constructs, or they are just like a continuum?
I'm not sure I understand your
Yes.
question.
For example, that one, the T2 variance, in that case, that is the variance compared to T1,
Yes.
and for T3, that's the variance compared to T1 again? Or
Yes.
Okay.
Yes. Yeah, everything is relative to 1. So like if you called this 10, then these would be like 11 something and 12 something. Like it would all just adjust. Like everything is in relative terms for this. Yep. All right. So note that I did not show anything with respect to the intercepts or means in this output because these are not on the same scale yet. That's the next layer of constraints, is to figure out if changes in the factor mean were responsible for changes in the observed variable means over time. That is coming next week. I must have been smoking crack to think I was getting through this handout today. But, you know, that's what happens when you haven't presented something before. I have no idea how long it's going to take. But it's fine, because now I'm prepped for next week. Woot! That's why I really like it when everyone asks questions. Not just because it's more fun, but because then it's like, oh, I'm ready for Tuesday now. That's a good feeling to have going into a weekend. Anyway, 1:44. Any last minute questions before we call it a week? Nope, we're good for now? Okay, then I will let you know if I have anything ready for next week. You have a formative assessment to work on, due Monday night. Hope to see everybody on Tuesday. Have good weekends. Thanks for being here. Bye,
Actually,
rumors,
Lisa, I
like
do have a question.
Oh, hit me.
Like, what, in the context of like CFA, like, what is a design matrix? Like,
Oh,
what's in a design matrix?
I was thinking of it in terms of just like standard regression, where you would have like your X matrix, where the first column has to be a 1 to multiply the intercept, and the next column would be the first predictor and the second predictor.
Oh,
Yeah, that's what I was thinking of, but since it's latent variable land, I think you'd have to come up with another terminology for that.
okay.
But the column of ones is like in matrix notation is how you say put the intercept or the mean in, because that's the
Oh.
column that term would multiply.
Okay, I'm very confused about what like a design matrix is, but that's helpful. I also have like another question about like the bifactor setup.
Yeah.
So if like originally we intended for the specific factors to be sort of like these method factors that like account for like whatever is not the other factor, like how does that work in the context of like a scale where they say like, oh, these specific factors are like sort of like the subscales and the general factor is like the concept generally? Like that just doesn't make sense to me.
So when you have multiple subscales that are thought to measure like one overlying thing, that will be consistent with a higher order factor model, not a bifactor model where the specific factors are uncorrelated with the general.
Yeah, so I was like reading this paper about like this scale measuring like intolerance of uncertainty, and they fit it to a bifactor model, and they said, okay, we have these two, and like maybe I'm misinterpreting what they said, but like they said, okay, we have these two specific factors. One is like inhibitory anxiety, and one is like something else, I don't remember. But you can score this as either like these two specific subscales or as like a general, you can just sum all of the items for, okay.
No.
Okay, because I was like so confused about like
No.
then like what the specific factors meant, and like it just didn't make any sense in terms of the construct, so.
No, you can't even add stuff together unless you have a parallel items model, which they probably didn't have. So that's wrong. But no, the idea of a specific factor, its intent is like, it's to clean up like the messy leftover correlation pattern you didn't want but got stuck with because of positive wording or whatever, like more specific things. But the interpretation of the specific factor as the crap left over is contingent on the pattern of loading supporting that interpretation. And I don't know that a lot of folks pay attention to that aspect of it.
Okay.
And if
Gotcha.
they didn't, like then it becomes ambiguous as to what's the primary and what's the crap left over. If the loadings for the crap left over are higher than the primary, like that's a problem.
Right. And like how can we know what the crap left over is? And like how can, yeah.
Well,
Okay.
so to know what a factor is, then you're heading into validity territory where it's like, what does this thing relate to? And if it shouldn't relate to anything unless like, I mean, I don't know what the crap leftover should relate to. Let's put it that way. It's hard for me to come up with a construct validity argument for that.
Yeah.
But
Yeah.
I would say the loading pattern and the relationships with other things are the only way that you can try to say theoretically what this source of variability is. But I don't think that just because they fit two different models, that means you add shit up and call it fine. I don't think that's consistent.
Okay, so it doesn't even really make sense to think about like constructs per se in this way, like with these specific factors as like part of a more general construct or anything
Yeah,
like
so
that.
the idea of a specific factor in a test that has multiple subscales is even weirder, because what is the thing that's not the general? Like,
Right.
like that like it's a very ambiguous way of thinking that I don't think that makes sense in a lot of cases.
Okay.
I'd have to see exactly what they're doing, but I don't think of those as comparable models. I think of them as just two different, they're different solutions for different problems.
Okay, yes. No, that's helpful. Okay, thank you.
Question, T, so I'm still recording. Do you
Uh-huh.
want this conversation on YouTube, or do you want me to cut the video before we have it?
It doesn't matter to me. I might have misrepresented that paper that I read, but I didn't say what it was, so
Yeah,
it doesn't
well,
matter.
it doesn't matter. It's X and Y or whatever. It doesn't matter to me, so.
Yeah.
Okay, well, I'll leave it on there.
All right, thank you.
All right, see ya.
Bye.